Hello, welcome back to astronomy class. Today we're going to start chapter 13, which is the end of stars. I lied. Chapter 12, the end of stars. Not the end of the class, but it is the end of what's happening to a star in some cases, because we already learned what happened to some stars in the small case, like our star. When a relatively low-mass star like our Sun reaches the end of its main sequence lifetime and becomes a red giant, it has a hot compressed core and a cooler, bloated atmosphere, ending its evolution by gently expelling its outer layers into space, leaving a burned-out core as remains. In contrast, a high-mass star ends its life in an almost inconceivable violence. At the end of its short life, the core of such a star suddenly collapses. This triggers a powerful supernova explosion that can be as luminous as an entire galaxy of stars. The immense force of a supernova combines atoms into heavier elements, which are ejected into interstellar space. Such heavy elements become the essential building blocks for planets like our Earth. Thus, the death of massive stars can provide the seeds for planets orbiting succeeding generations of stars. In this chapter, we will look at the physical processes that occur when the most massive stars reach the final stages of their life cycles. After a cessation of the nuclear reactions that support a giant stellar core, a star's outer layers can rapidly dissipate, leaving behind a tiny crushed core that emits very little light as a neutron star or a pulsar. As we will see, it is not only the largest of stars that can end violently. A normally quiet white dwarf can suddenly flare up into an exploding supernova if it gathers explosive gas from a companion star in a close binary star system. But for the end of the giant stars, the end can be even more bizarre. Imagine, instead, a swirling disk of gas and dust orbiting around an object that has more mass than the sun, but is so dark that it cannot be seen. Imagine the material in this disk being compressed and heated as it spirals into the unseen object, reaching temperatures so high that the material emits X-rays. And imagine that the unseen object has such powerful gravity that any material that falls into it simply disappears, never to be seen again. These unseen objects with immensely strong gravity are called black holes. The matter that makes up a black hole has been so greatly compressed that it violently warps space and time. If you get too close to a black hole, the speed you would need to escape it exceeds the speed of light. Because nothing can travel faster than light, not even light, can escape from a black hole. Even more remarkable is the discovery that black holes of more than 1 million solar masses lie at the centers of most galaxies, including our own Milky Way. So that's just a little intro of what this whole section is about. We're going to start off in 12.1 with high mass stars that create heavy elements in their cores before violently blowing apart in supernova explosions. And as a result, they leave behind a bunch of remnants. So unlike the stars like that we were talking about last chapter, a star larger than 4 solar masses undergoes an extended sequence of thermonuclear reactions in its core and in the shells, including processes based on carbon, neon, oxygen, and silicon. So all we've talked about up until chapter 11 was hydrogen fusion and helium fusion. We got hydrogen fuses into helium, helium fuses into carbon, and then it stopped there because stars like our sun do not have any more, they're not massive enough to make anything else. Here we see the high mass stars can fuse carbon into neon, can fuse neon into oxygen, and can fuse oxygen into silicon. Here we see an example of the mass lost from a supergiant star. Star is losing its mass at a rapid rate in a strong stellar wind. As this wind collides with the surrounding interstellar gas and dust, it creates the bubble shown here. So that star all the way in the center is creating that gigantic bubble out there, somewhere in space. Here's an example of what we're talking about in this chapter. You look at the top, it says evolutionary stages of a 25 solar mass star. That means we're talking about if we could stack our sun 25 times, put that into one star, and this is what it looks like. This is its life cycle. We see that it goes hydrogen fusion, helium fusion, carbon, neon, oxygen, silicon. After silicon, we see it no longer fuses anymore. We see something called a core collapse, a core bounce. Finally, the explosive supernova. It gives you the temperatures here. . 1, 2, 3, 4, 5, 6. So, ooh, I can't do math. 1, 2, 3, 4, 5, 6. So 40 million Kelvin? Ooh, let me double check this. $4 million. I'm sorry. Okay, so you can see the core temperature increases here by a factor of 10. So this isn't half right here, even though it goes from 4 to 2. This goes from 10 to the 7th to 10 to the 8th, right? So that means you're multiplying it by 10. So it's 10 times hotter, and then this is negligible compared to that. You see, this is 3 times hotter, and then it goes 10 times again, and all these stay up here until we get to the core bounce. And the core bounce is 10 to the 10th. That's a gigantic number. Here we see the core density, 5 times 10 to the third, 7 times 10 to the fifth, and it gets bigger and bigger and bigger and bigger and bigger and bigger. Keeping in mind that the more dense something is, the smaller it is. So this core is shrinking. It's being compressed and compressed and compressed. So much more matter is fitting in the same amount of space. So it's getting compressed and compressed and compressed. And you see the core density varies on the supernova. Here we see the duration of the stage. That's 7 million years. This is 700,000 years. And then it switches down all of a sudden to 600 years. There's only enough carbon in there to fuse for 600 years. So this is, like, from here down is actually pretty interesting compared to what we've been learning, how hydrogen and helium take, millions or thousands of years. Carbon fusion, there's only enough to fuse for 600 years. And for neon, there's only enough to fuse for 1 year, and then for 6 months. For silicon, it can only do that for 1 of our days, and then it runs out of fuel. The core collapses in 1/4 of a second. The bounce, which we'll learn about, and happens in milliseconds. And then the whole supernova takes place over 10 seconds. So all of this time is undone in a matter of 20 seconds, not even 12 seconds. That's insane. So let's look at this. If the core of our sun was compressed to a much higher density and able to maintain a temperature of 1.5 billion kelvins in its core, what would happen to the helium in its very center? Well, if we look over here, 1.5 billion is right here. 1.5 billion is right here. So if our sun's full of hydrogen, it'll undergo hydrogen fusion to helium, and then to carbon, and then to neon, and then to oxygen. And it will fuse, at this point, it fuses oxygen into silicon, but the silicon can't fuse. That's what it's saying here. We could finally get to silicon, but we would not fuse silicon after that. Now, remember when stars enter the giant phase, what's happening is there's hydrogen fusion on the shell, right? So thermonuclear reactions can take place in the shell and in the core. But what's happening with these stars is that there's multiple types of shells. So thermonuclear reactions can take place simultaneously in several different shells surrounding the core. And energy is released at such a rapid rate that the star's outer layers expand tremendously, resulting in a supergiant star whose luminosity and radius are much larger than those of a giant. Much larger than those of a giant. Here we see an example of the composition of one of these supergiant stars. Notice this right here, it says Jupiter's orbit. That's not the size of Jupiter. That's Jupiter's orbit. That's how far Jupiter is away from the sun. That's how big this star is. That is massive. That is insane. If you put this star in our solar system, it would completely obliterate everything up to Jupiter. That's how large the star is. We see on the very outside, on the coolest part of the core, there's hydrogen shell fusion, and then helium, and then neon, and then oxygen, and then silicon, and then in the middle you'll see iron core, which was not in this graph. You don't see iron anywhere here, because iron does not fuse the same way. Let's see if it's here or if it's later. It explains why. There's basically no types of reactions that will happen once you get to iron that will produce energy. So this isn't going to take place anymore. The fusion won't take place with iron. All of these guys can fuse, but iron will not fuse. So you just get left with the lump of iron in there. You can see why that might be a problem. Remember last chapter, as we're squeezing the core, the carbon core of last chapter, we got that electron degenerate pressure, and then eventually the star gave off some thermal pulses and ended up as a white dwarf. Imagine that happening, but instead of carbon, we're a couple farther layers down into iron, and iron cannot fuse. Like, it doesn't matter how hot you get, it's not going to fuse in this case. We see that here, it's not here. So how long does the neon fusion stage last in a sun-like star? If we just look here, neon takes 1 of our years. Oh, dang it! This question got me. This question got me. Hopefully it doesn't get you guys. How long does the neon fusion stage last in a sun-like? I even looked at this before I presented this and I forgot. A sun-like star. Our star is not 25 solar masses. Ours is only 1. So it's a trick question. Our star, our sun-like star, cannot even have neon fusing. A sun-like star can only fuse hydrogen, maybe helium, but that's it. In the last stages of its life, then, a high-mass star, that we're talking about, these gigantic ones, has an iron-rich core surrounded by concentric shells hosting the various thermonuclear reactions. Once a star's core is converted into iron, no more energy-producing thermonuclear reactions are possible, and the only source of energy, then, is contraction and rapid heating. Because remember, if you squeeze something, it's like heating stuff up. A star with an initial mass greater than 8 solar masses dies in a violent cataclysm in which its core collapses and most of its matter is ejected into space at high speed, producing a core collapse supernova. A core collapse supernova. Now, this part is, I don't want to say entirely speculative, but it's a theory. And we're not 100% sure on this, but we have some models, we have some science, there's been a lot of math, and this is what we think kind of happens during one of these supernovas that this slide was talking about. So we have the shells, right? It says an onion-like structure. Hydrogen's on the outside, then helium, carbon, oxygen, silicon, and then iron in the middle. We know iron does not undergo fusion, so the core becomes unable to generate heat. Which means if this cannot generate heat, the entire core itself will kind of shrink down a little bit. Okay, so as the gas pressure drops, all of this material starts rushing in onto the core. Okay, so the core is collapsing. The iron core can't make any heat, so it's shrinking, and because it's shrinking, everything is collapsing in onto the core. Within a second, the core collapses to nuclear density. What that means is the stuff squeezes the iron so hard that it stops it from being iron and breaks it into essentially electrons and protons, but then all the electrons and protons squeeze together and become neutrons. That's what it means by nuclear density. You squeeze it so hard that all of the atoms, all of the subatomic particles just become neutrons. Inward falling material rebounds off of the core, setting up an outward going pressure wave. So once you squeeze that core into being that gigantic ball of atomic particles, it's almost physically, even breaking these rules, it's almost physically impossible to squeeze it any farther. And because of that, it squeezes just a little bit and then bounces back very, very like rigidly. And it sends a shock wave through the star this way. Okay, so it sends like a pressure wave. Everything collapsed on it. It squeezed it to subatomic particles. It bounced just a little bit, but that sent out a shock wave or a pressure wave going this way. Okay. Oops. Neutrinos pouring out of the developing neutron star in the middle propel the shock wave outward unevenly. So not only is there a pressure wave, there's a bunch of neutrinos, because remember when you start combining subatomic particles, you get those little guys, those neutrinos, that they're so tiny that they're passing through you and you can't even tell. Well, there's so many of those, and there's so much light and everything, that those themselves are propelling a wave out, while all of this stuff is still falling in. So that makes this crazy, like, bunch of bubbles. Right here you see a neutrino heated gas bubble. A bunch of uneven bubbles. The material's pushing in, the neutrinos are pushing out, and eventually the shock wave sweeps through the entire star, and it blows it all apart. And this is what we think is happening in one of these core collapse supernovas. Heats up so much that the iron core cannot. It heats up so much that it fuses into iron. Iron cannot fuse, so it stops producing heat, which means everything squeezes in on it. As you squeeze iron into it, you squeeze it so hard that it becomes nuclear density, meaning everything just turns into a ball of neutrons. As it does that, it shoots out a bunch of neutrinos, and it got squeezed just so hard that it let out a little rigid shock. That shock goes outward, combined with all this stuff rushing backwards, creates this shock wave that essentially rips all the star apart, except for that little center that we'll talk about. So then this question is saying, is a supernova resulting from the death of a star an outwardly directed explosion or an inwardly directed explosion? And the answer is both. Because remember, the outer layer is falling down to like squeeze the core, but then once it does that, the core bounces back as everything is falling down still. So it's a little bit of both. First it's an inward, and then it's an outward. Supernova can have a maximum luminosity of greater than 10 to the 9th times larger than our star. Okay, 10 to the 9th, not 10 times, not 900 times, but 10 to the 9th times brighter than our sun. That is crazy intense. Here we see a star. Sorry for the bad picture, but there's a star right here. 12 days later, we happened to get lucky, and it became a supernova. That's how much of a difference it makes on this picture. It's just this gigantic white blob. Here was a picture before a supernova, and then after a supernova, we get this really bright light. And we see here, people in the southern hemisphere could see the supernova without a telescope. So if it was nighttime, this you can actually see the supernova. You don't even have to use a telescope. That's how bright it was. But that was what, in 87, so before any of us were born. Even me. I'm not that old yet. Here we see an incredibly cool supernova. Here's like an artist rendition, but here is what it actually looks like to us. You see like this ring right here, this ring right there, and then the inner ring. It says the inner ring is 1.3 light years across, which means this light takes 1 year to get across to over there. That's how big this thing is. What we think happened is that there was supergiant gas right here, red supergiant gas that kind of constricted everything. So once that the supernova happened, this gas kind of prevented everything from expanding perfectly, so instead all this stuff expanded outward, all this stuff expanded outward, and we get this cool hourglass looking thing because of this ring of gas kind of constricting the middle. And if that wasn't there, if that ring of gas wasn't there, it probably would have ended up as a circular cloud of dust instead of that cool hourglass. Oh cool, that's it for section 12.1.